Hi, so today I'm going to talk about the problem-solving methods in reinforcement learning. So we could divide into three main problem-solving methods for reinforcement learning. So the most classical solution method is the dynamic programming, which requires a problem associated with a Markov decision process, which basically means, which is basically a model-based approach. And this model-based approach means that in reinforcement learning, model means the state transition function and the reward function. So in a Markov decision process associated problem, we assume that we know everything about the environment itself, which enables a dynamic programming approach in solving the problem. So we know that the dynamic programming is basically we have a large problem and we divide it into small sub problems, and also we know that the big problem, the large problem, has an optimal substructure, which means that when we divide the large problem into small problems, if we calculate the small problems and get the optimal solution for them, then those, it's like a divide and conquer. So if we get the optimal solutions for the small problems, that will lead, combining those will lead to the optimal solution for the large problem, the problem of interest. So basically, since we are assuming that we know everything, which means that we know the transition function and the reward function, we're technically not learning. We are so instead of actually making an action and getting a feedback from the environment, that's not the case here. Since we already know the reward function and the state transition function, we could estimate what would have happened if we took this action. So we don't have to actually learn by actually acting. We are estimating. So in basically we could say that we are planning instead of learning. And so how do we estimate? What do we estimate? We estimate the next step's value function to update this state's value function. So it's basically a concept of bootstrapping. So in reinforcement learning, when we come up with the term of bootstrapping, it means that in updating, we are using an estimate. So for this case, to update this state's value function, we are using the estimation of next state's value function. So that's where the bootstrapping property comes in. So with this dynamic programming approach, as in any other problem-solving method for reinforcement learning, there's a prediction part and a control part. So a prediction part is basically, like for example, we are given a policy, let's say it's policy A, and we predict the value function for that policy. And then the control part is now finding the optimal policy among the policies, the multiple policy, like value functions associated with multiple policies calculated in the prediction stage. So that's basically the two-step process which will be done in the dynamic programming. But as we know, the dynamic programming approach can be only applied in the Markov decision process associated problems, which means that we have to know everything about the environment. So this is for real world problem. This is infeasible because there are not a lot of cases that we know everything about the environment in a real world setting of where we want to apply reinforcement learning. So basically, dynamic programming is only tested out for toy problems. So, okay, so this is an analogy. So we know the AlphaGo, which is an AI, a Go playing AI made by the Google DeepMind. And let's say that, so playing Go is basically for every time step. If we say an episode for a Go will be the start of the game of Go, and the end of the episode will be the terminal state of the Go, which means either one loses, resigns, and the one party wins. So at each time step of the game of Go, in point of view of the AI, it wants to know which move. Basically, it's not a move because it's not chess, it's a Go. So the AI wants to know where to put the rock, like I mean the piece. And if we use a dynamic programming approach, we basically have to know all single possibilities. Oh, we have to combine, like, it's not only about putting here or there. It's I believe it's a 19-to-19 grid. It's not only about one time step. It also has to know what would happen if I put the piece, for example, at this point. There would be so many combinations. So it is impractical to apply dynamic programming to like making in terms of AlphaGo, because so many cases. So in this case, AlphaGo instead used an approach called a Monte Carlo method, which is, in essence, Monte Carlo method comes from the Monte Carlo simulation, which is basically generating sampling random samples and then trying to deduce something meaningful from there. So in context of reinforcement learning, Monte Carlo method is basically aiming not to sample, not to know about everything, but advancing to one direction. So it may not lead to the optimal solution, which the dynamic programming would, but infeasible, but it still could lead to a good estimation. Like it would lead to a suboptimal yet effective solution. So more formally, the Monte Carlo method in the reinforcement learning doesn't require the MDP environment. It doesn't have to know the state transition function or the reward function, but it samples randomly. And then one more point to note is that it doesn't only sample one step, but it has to sample until the terminal state of that episode, that gameplay. And then it averages the rewards out of it. And like, for example, let's say the value function, so the initial time step, let's say the time step as 0. And let's say that the terminal time step of this gameplay episode is 20. Then from step 0 to step 20, each step should have associated value function depending on the state. And that the value of that value function will be based on the average of the values onwards to the terminal. Like, for example, if you want to know the value function for time step 15, then that would be the average value of the value functions, estimated value function, not estimate, it's sampled value functions from 16 to 20. And the value function for 5 would be the average value of the value functions from 6 to 20. It happens like that. So since we're actually sampling instead of using some estimate as we did in dynamic programming, this is not using the bootstrapping method. Okay? But the problem of this like, for example, for Go, they used this Monte Carlo method because they're basically were using a supercomputer which could afford that, and they were actually playing against the world champion of Go. So they did have a motive to actually try out this this pretty computationally heavy approach. But for normal settings, because this Monte Carlo method requires the update to only happen after the complete episode, the convergence is slow, obviously, because we have to wait until an episode ends. And which is a problem that which the dynamic programming didn't have. So now we know both the limitations of the dynamic programming approach and the Monte Carlo method approach. And to again clarify, the problem for the dynamic programming approach was that it is possible to learn online, which means that step by step, because it's basically using the optimal substructure incrementally. It's calculating the solutions for the subproblems incrementally to combine it into and get the solution for the global solution, optimal solution. So it's basically, since they're doing it incrementally, it's online learning. It's an online setting. But it is infeasible because you have to know everything. That's the disadvantage of the dynamic programming. And the disadvantage of Monte Carlo method is that basically you have to wait until an episode ends to calculate the average of those, to update each the value functions for each time step, you have to wait. So that which leads to slower algorithm convergence. So that's the disadvantage. So to kind of combine those two, dynamic programming and Monte Carlo method, it leads to an algorithm called a temporal difference, which is basically capable of learning both online and offline. And okay, so first of all, let's try to compare. Okay, the temporal difference learning has an advantage over dynamic programming, that it doesn't have to know everything about the environment, which in this case, temporal difference learning inherits the advantage of the Monte Carlo method. That's the comparison between the temporal difference and the dynamic programming. And to compare temporal difference and the Monte Carlo method, the temporal difference has an advantage that it can learn from an incomplete sequence. It doesn't have to wait until an episode ends, which happened in the Monte Carlo method setting, which was its disadvantage, the biggest disadvantage, which led to slower convergence. So you can see that the temporal difference learning is basically trying to inherit the advantages from each the dynamic programming and the Monte Carlo method, while trying to discard the disadvantage from each of the two. So basically, the temporal difference learning also has some variation of, so not going to go over the actual equation, but one thing to note is that the temporal difference learning has hyperparameters of a lambda, which is basically this lambda denotes the step of temporal difference learning. So the temporal difference learning is basically you can think of it as a Bellman equation, okay? So we know that the Bellman equation in terms of the reinforcement learning setting is updating either the value function or the action value function based on the addition between the immediate reward and the estimation for the next state, the estimation for the value or action value for the next state. So again, here's this estimation property, which we saw in the dynamic program setting, which means that this temporal difference learning is also bootstrapping. So it's not sampling, but it's estimating. So it's bootstrapping. And again, so as I said, there's a variation of property in this temporal difference, which the most, so the regular Q learning is basically following a one-step temporal difference learning, which means that, okay, so to try to explain this, as I said, in the Bellman equation, the left-hand side is let's just assume that we are interested in the value function instead of the action value function, okay? So the value function for this state, which we aim to update, will be the left-hand side of the equation, Bellman equation. And the right-hand side of the Bellman equation will be the Bellman error. And the Bellman error will basically be composed of two terms, a subtraction of two terms. And the first term is the target, the Bellman target, which is composed of the immediate reward from taking some action added by the estimation for the value function for the next state. And this value function for the next state is an estimation, but however, the immediate reward from this action is not an estimation. It's actually what the environment gives as a feedback by actually making this action. So this, you could understand it as a real value. It's not some kind of estimation. So by this real value, the model is still grounded. So it's basically reflecting the reality property lies in this reward, immediate reward, which actually reflects what happens instead of estimation. And so when the lambda is 1, which means that in a one-step temporal difference learning, we only use the immediate reward by making one step, which means that the reality factor in this whole equation is only confined to one time step, which is still what makes it grounded, but because we're relying only on one time step, naturally the convergence will be, the model will be biased to this one step. However, if we then in this case, if we want to deal with this bias problem, we could add more terms. Like instead of updating the left-hand side of the equation, which is the value function for this state, immediately after one step, we could accumulate the immediate rewards for one time step ahead and what two times step ahead and so on. So that's where the hyperparameter value comes in. So we talked about another version of this temporal difference learning was an n-step temporal difference TD learning. So for example, if we're assuming a 3-step TD learning, the reality factor, which is the immediate reward, we are accumulating into one time step ahead, two times ahead, and three times step ahead. By doing this, we could actually, now the model not only depends on one time step reality factor, but now it depends on reality factor of 3 time steps. So naturally, the bias coming from relying on one time step reality factor will decrease. So by doing that, the model will be more stable. However, one fun fact is that if this n step, the n is here the hyperparameter, if this n becomes as long as, like, let's say the episode has 20 time steps as we assumed before, and if this n becomes 20, it's exactly the same as the Monte Carlo method. So it's basically doing some Monte Carlo method because okay, so what differentiates between the Monte Carlo method and the temporal difference method, we can think of as while the Monte Carlo method doesn't have any estimation, it's all samples. The TD learning is composed of a sample factor and estimation factor, and that the ratio between the sample factor and the estimation factor is controlled by this lambda, which is basically our n when it comes to n step. So when the length of the number of time step in this whole episode is 20, if the n is 5, then the reality factor is 5, and the estimation factor is 15. But if n dominates, which means that when n becomes 20, the reality factor becomes 20, and the estimation factor becomes 0, which is exactly what the Monte Carlo method is doing. So it's basically, yeah, as I mentioned, if we kind of draw it as a line and dynamic programming being in the leftmost and the Monte Carlo method being in the rightmost, temporal difference learning, TD learning, is somewhere in between, like depending on the hyperparameter lambda. So that's the intuition. But as we know, so I mentioned that the bias coming from a one-step TD learning can be dealt with by increasing the n, which is virtually increasing the reality factor in the model. However, if we increase it to n, or like, which means the whole episode length, or even very close to it, now, as we know, there in machine learning or like a deep learning, there's also always a bias variance trade-off issue. So if we increase it to n as the whole size of the episode, then the bias problem will be resolved. But however, it would lead to a huge variance issue, because basically in this setting, in the reinforcement setting, the variance issue is basically coming up with different policies depending on which state happened. Like, for example, from state 1 to state 20, what the resulting policy will basically, like, a huge part will depend on the what was the initial value of state 0. Depending on the state 0, like, for example, so if you could think like this, in this TD learning setting, so let's say that you're driving somewhere, and there could be lots of small incidents, like the traffic, or like there should be some places where it's hard to make a curve, or like there's lots of factors that might affect in each state how fast are you going to arrive at your destination point. So in Monte Carlo's method setting, it's basically calculating each time step value function after you arrive at the destination point. You're averaging out, which is accurate, but takes a long time because you have to wait until you actually arrive to the destination point. But this TD learning is more like, let's say that there's for example, there's a road that's usually like a tunnel, where it usually takes a long time to actually exit from. And for some reason today, you came out earlier from the tunnel than usual. Then now, based on that, oh, today I got out of the tunnel faster than I expected. So now I can estimate that my arrival time will be earlier than what I thought. So that's basically where the estimation part comes in, and the update. So the update is happening while you're running, is even before you actually arrived at the destination point. So that's a TD learning. But the problem in this, okay, so back to the Monte Carlo setting. The problem of this Monte Carlo setting, for this analogy, for this example of destination arrival car riding example, is that based on where you start, the initial, where you start driving. So there's no such uniform state. It's randomly picked. The states and the result, because it's only the model is only depending on the real factor. There's no estimation factor, which means that there's no such averaging out effect now in this only real factor using model. So for take 1, for drive 1, you would take 40 minutes because you started as location A, which led to this crazy road. In another initialization, which you start in another state, then now the environment is different, so you would arrive much faster because of the feature of that environment, the characteristic of the environment. So this means there's no averaging out, and there's no averaging out because there's no estimation factor. It's only all models are depending on a real factor. So now you can see that there's a huge high variance problem. So in other words, Monte Carlo method has a high variance, low bias. Monte Carlo method is high variance, low bias, and temporal difference learning, which the most extreme temporal difference learning is one step. One step TD has high bias but low variance. So that's the trade-off. So, and we know that the TD method is basically what led to, and is also possible of doing online learning and offline learning. And it's basically the generic idea behind the Q learning, or like SARSA, which state action, reward state action for next state. So basically the subsequent problem solving methods, like the algorithms, are mostly, a lot of them are based on this TD learning. DQN is a part of it, and so on. Thank you.